In this lecture, we'll give the term and recursive forms of the geometric sequence. We'll show the geometric sequence follows along the exponential curves and consider its limit. We'll move on to geometric sum, and we'll give explicit formulas for that. Next, we'll look at the geometric series, which is the infinite sum, and give formula for that as well. Lastly, we'll solve first-order linear recursive equations in terms of these sums. Let's start. A doctor travels to a village to treat a patient with a miracle drug. But the doctor there is bit by a mosquito carrying malaria. On day 0, she was infected by C parasites, and each parasite doubles in her body daily. The growth from one parasite, i.e. when C is equal to 1, looks something like the following. After day 0, there would just be that 1, but then that 1 would become 2 after day 1, and the 2 would become 4 after day 2, and the 4 would become 8 after day 3. And this doubling goes on and on. So the initial C parasites would become 2C after 1 day, 4C after 2 days, etc. After n days, the doctor is infected with AN, which is equal to the initial contraction C times 2 to the n. This doubling is somewhat arbitrary. If on average each parasite split into some real R greater than 0, the same formula would arise. We would just have R in the place of 2. Another example is AN is equal to 5 times 1.5 to the n. So initially there were 5 parasites, and on average 2 parasites would split into 3. So only one of the 2 would split. These points then follow along an exponential curve scaled to start at 5. The base would be 1.5, as it would be R in the geometric sequence. And the points in the sequence would just occur for the integer values of x, which we also label n. So here you can see that we have the exponential curve, and we can plot the points of the geometric sequence along that, labeling the y-axis, the vertical axis, as A, designating the starting point A0 to be 5, and A1 is equal to 5 times 1.5, or 7.5. And then we plot the other points here from 2 to 7. Now how about this miracle drug being delivered to a patient? Can this be described by a geometric sequence? The answer is yes. Let's look at the patient's drug concentration, where the initial starting concentration on day 0 is C, which is attenuated by a factor R daily, where R is between 0 and 1. So after n days, the concentration of the drug that remains in his system is AN, which is equal to C times R to the n. So an example would be that AN is 100 times 0.5 to the n. Here R is less than 1. So this also could be plotted along a scaled exponential curve. It would be scaled to start at 100 instead of 1, and it must have base equal to 0.5 because that's what R is. So we plot here the exponential curve scaled 100 times 0.5 to the x. And then along that we can plot AN with A being on the vertical axis and both x and n being on the horizontal one, and applying only at the integers. So it would start off at 100 at A0, and then A1 would be half of that, which would be 50. A2 would be a quarter of the 100, which would be 25, and then 12 and a half, etc. And we've marked these points along the curve. Alright, so we have 2 examples now of this important type of sequence, which is called a geometric sequence. A sequence AN is geometric if it has this form. AN is a constant C times R to the n for some real C and R. In its recursive formula, AN plus 1 is equal to R times AN. You take the previous term and multiply it by R to get the current. And of course we have to start that up with some initial value C. Now that we've defined the geometric sequence and shown that they follow the exponential functions, possibly scaled, we can look at the limits of geometric sequences. So the simplest case is when R is equal to 1. In that case, the next term is equal to the current one for all n, and so the limit is obviously equal to this initial value C. The next simplest case is when c is positive but r is strictly larger than 1, since then the exponential function with base r is increasing. And if we multiply that by the c out in front, which is a scaling, then we still have an increasing function. And so the geometric sequence which follows this scaled exponential function is also increasing. Unfortunately, it's not bounded above. This means that the sequence diverges to infinity, since there's no upper bound. The next simplest case is where c is still positive, but r is less than 1. In this case, the exponential function r to the x is decreasing, as is r to the n when we're just looking at the integer values. If we multiply c by r to the n, since c is positive, that will also be decreasing. But this one is bounded below by 0, since the exponential function r to the x is also. And so we have a sequence which is decreasing and bounded below. The tightest bound below is 0, so this limit will be equal to 0. In the two cases that we considered with positive c and r not equal to 1, the positive c translated into a positive sequence. When we take the analogous case with c negative, so we're starting with some negative value, the sequence is always negative. It's the mirror image of the corresponding case with c positive, reflected in the x-axis. And the result of this mirror imaging, in case r is greater than 1, instead of going off to positive infinity, we go off to negative infinity. We diverge to minus infinity. And in the case r is less than 1, we still converge to 0, but we do so by approaching it from below rather than above. r is 0 is trivial. The first term and beyond are all 0. Finally, the case where r is negative will result in an alternating geometric sequence. This makes it a little bit more complicated to analyze, but what happens is we have divergence rather than divergence to positive or negative infinity, and this occurs when r is less than or equal to minus 1. When r is between 0 and minus 1, not including minus 1, we do have convergence to 0. Returning to the story. While the doctor keeps returning and keeps getting bit, on each day the doctor is given c new parasites. Meanwhile, the existing parasites just keep doubling day after day. Let Sn denote the total number of parasites in her body after day n. Then this would be equal to the number of new parasites c plus 2 times the number of parasites that were in her body after day n minus 1. And this has to be good for every single day. N is 1, 2, 3, 4, 5, etc. We could use this equation twice to find that Sn is equal to c, the new ones, plus 2c, which is the parasites that resulted from yesterday's bite, plus 4 times Sn minus 2. That is 4 times all the parasites in her body 2 days ago. And we could continue this process to find that Sn is equal to c plus 2c plus 2 squared c plus etc. right up to c times 2 to the n. And we call these then the different terms a. So the first one would be a0, which would be c, a1 would be 2c, etc. What is the value of Sn? In other words, how many parasites does she have in her body after day n? Well, let's be optimistic and take the case where c is equal to 1 and recall that r is 2. And let's take the case where n is 3, so we're considering after 3 days. Well, we have the 1 that was newly introduced on day 3, and then we have 2 that came from the bite on day 2, and then we have 4 that came from the bite on day 1, and then we have 8 that came from the bite on day 0. So if we add them all up, we will find, and we've numbered them here, that there are 15. Now this brings me to something that's really cool that I want you to remember. So when we added 1 plus 2 plus 4 plus 8, it was the next term, which would be 16, minus the first term. And this is going to turn out with minor modification to be true for geometric sums in general. And in particular, if we go to the general case where c is not necessarily 1, the total number of parasites after n days is c times 2 to the n plus 1 minus c, i.e. Sn, which is equal to c times 2 to the 0 plus 2 to the 1 plus 2 to the n minus 1 plus 2 to the n is equal to c times 2 to the n plus 1 minus 1. And once again, that's the next term, an plus 1, minus the first one, which is a0. Now let's go back to the patient scenario, but this time the patient is benefiting by getting a new dose C every day. This means the drug is building up. So in particular, whatever was in the patient's body after n-1 days, we'll call Sn-1, was then attenuated by a factor R, but C was added to it. So Sn then is C plus R times Sn-1. And we can just go through the process we went before with the parasites to find Sn, the total concentration in the body after n days, is C plus Cr plus Cr squared plus Cr to the n. The recursive form of this would be Sn is equal to R times Sn-1, subject to this ongoing dose, S0 is equal to C. This brings us to the general form for the geometric sum, which we just gave an example of for the parasites. So suppose that R is a real number and an plus 1 is equal to Ran. That is a situation where we have a geometric sequence. And then we want to sum it to form the geometric sum. So we say Sn is the sum of the 0 first all the way up to the nth term. Well, this sum is equal to one of two things. If R is not 1, then the sum is A0 minus an plus 1 over 1 minus R. And what I remember is this is equal to the first term minus the next term, the one that doesn't appear but would come next, to all divided by 1 minus the multiplier. And in the case where R is equal to 1, we just have that the sum is n plus 1, that's the total number of terms, times a0. Let's take a couple simple examples. Suppose we wanted to sum 2 minus 1 plus a half minus a quarter plus an eighth minus a 16th. Well, we could recognize that you get each successive term by multiplying the previous one by r is equal to minus 1/2. Hence, this is a partial geometric sum, and our formulas apply. So we need the first term, which is a0, which is 2. And we need the next term, which would be minus 1/16 times minus 1/2, or 1 over 32. And so via the formula, we have the first term 2 minus the next term minus 1 over 32 over 1 minus the multiplier, which is equal to minus 1/2. And so we're left with 2 minus 1 over 32, all multiplied by 2/3. After simplification, we get 21 over 16. Let's take another example. 5 times 6 to the 3 plus 5 times 6 to the 4 plus 5 times 6 to the 5 plus 5 times 6 to the 6. Going from one term to the next, we're just multiplying by r is equal to 6. The first term is 5 times 6 to the 3, and the next one that isn't in the sum is 5 times 6 to the 7. So via our formula, the first term minus the next term over 1 minus a multiplier is, the sum is 5 times 6 to the 3 minus 5 times 6 to the 7 over 1 minus 6. Notice both the numerator and the denominator will be negative in this case, which is common when r is greater than 1. And then this just simplifies, because the bottom is 5, so it'll cancel with the numerator 5s, to 6 to the 7 minus 6 to the 3.